Okay.
Okay, hello everyone. Welcome to HO Program. Our today's speaker is Vibhuti Kumar Jha from Southwest Research Institute. Dr. Vibhuti Kumar Jha got his PhD from Indian Institute of Astrophysics, Bangalore, India in 2022. And his thesis was on the long-term study of the sun and its implication to solar dynamo models. Currently, he is a postdoctoral researcher at Southwest Research Institute, Boulder, Colorado, and working on incorporating the far-side helioseismic observations of active region in the surface transport model. His research interests include development of automatic algorithms, surface transport models, machine learning, etc. He is interested in public outreach activity, teaching, and photography also. Vibhuti Jha, he will be speaking on today. He will be speaking on the tilt of bipolar active regions beyond Joy's law.
Thank you, Mosmiri, and thank you for inviting me, and thank you for your kind introduction. So just making sure that everyone can hear me properly online. Okay. So today I'll be going to talk about the tilt of bipolar active region. We all are familiar with the Joyce law, but I will be talking slightly beyond the Joyce law. And I will come to that why this title of this talk is in this way. So let me first start with just basic introduction, and I'm sure that everyone know about what bipolar active regions, but just for the completeness, we all are familiar with the sunspots, and we all know that the sunspots are actually the region of strong and concentrated magnetic field when you look at the magnetograms. So in the magnetogram, these regions look something like this. And if you join the centroid of the positive and negative polarities, here the two colors represent the two different polarities of the magnetic field. One is towards us and another is away from us. If you join the centroid of these two polarities, what you see is that, interestingly, the line joining the centroid is actually tilted with respect to the solar east-west direction. And that is, by definition, the angle between these two lines is called the tilt. So here you can very easily notice that delta theta that represent your difference in the latitude, and delta phi is the difference in the longitude of the two centroid, and cos theta there is an additional term that is just to take care of the spherical geometry of the sun, because you are calculating the tilt on the sphere. So in 1919, Hale came up with the observational study that suggests that the tilt of these bipolar active regions depend on the latitude of their emergence, and that is popularly known as the Joyce law today. And then mathematical equation that dictate this Joyce law is gamma equal to gamma naught sine theta, where gamma is the tilt and gamma naught is termed as the amplitude of the Joyce law. So that other way also, like we'll use the linear relation instead of the sine theta term, because for lower value of theta, small value of theta is very close to sine theta, is very close to theta. So that is Joyce law. So now, why we are so interested in this tilt? What is making these tilts so important? Why we are so interested in studying these tilts? So to understand that, what we have to look at this, I don't know, it's looking how it is looking for the onlines, but it's what is the magnetogram of the sun during the solar minima, and there is another magnetogram that during the solar maxima. So you can very easily notice that there are a lot of magnetic activity happening during the solar maxima, particularly at the global scale. And based on the historical observation and the modern observation, now we all know that the sun shows a very solar cycle, 11-year of periodicity in the solar activity, and that we call as solar cycle. And along with this solar activity variation, we also notice if you measure the polar field, what you notice is that the polar field is also changing with the periodicity of around 11 years. But if you consider the polarity, it is around 22 years. So that's why the Solar cycle is 11 years, but the magnetic cycle is 22 years. To explain this cyclic behavior, there has been many models that have been proposed. It's either surface flux transport, dynamo models, and many models have been proposed. But the fundamental idea behind all these models is that, if you consider during the solar minima, the sun is almost like a bar magnet. Your magnetic field is very poloidal. Then the differential rotation is wrapping, stretching, and twisting the magnetic field around the sun, and you get the poloidal field. And these poloidal field, due to magnetic buoyancy, comes out of the photosphere, and you see them as active regions or the bipolar magnetic regions. Now, another part of the story is that to complete the cycle, you need to convert this toroidal field back into the poloidal field. And here comes the Babcock and Layton process. And that suggests how these emerging active regions, which are tilted, can lead to the conversion of toroidal field back to the poloidal field. And the fundamental idea of the Babcock-Layton process is that, on the solar surface, you see the tilted active region, bipolar active region, and since they are tilted, there will be some residual flux. Because of the tilt, you will have some non-zero axial dipole moment, and that is transported to the pole. And first, it will cancel the adjusting polarity there, and then lead up to the opposite polarity. And this process, by this process, the toroidal field is getting converted into the poloidal field. Just to give you the idea about the importance of tilt, I'm showing you this image where I have done the simulation where I have started with the standard Joyce law. And then I have changed the tilt of all active regions slightly by 0.1 degree only. So you can see as I change the tilt, this cursor is not moving. So in this, as you go from top to bottom, I am changing the tilt by 0.1 degree. So if I change the tilt by just 0.1 degree on average, what you see how it is affecting the building up of the polar field. And I'm sure that everyone knows that for the solar cycle, how much importance polar field carries. So it is utmost important for us to understand the formation of bipolar active region, the tilt, and how it is interacting with the local plasma there. So now the first question, now we understood the importance of the tilt of the bipolar active region. The first question that comes is why there is actually tilt in the bipolar region in the first place. And in 1993, De Silva and Chaudhary came up with the idea based on the thin flux tube model is that when the flux tube is coming out of the photosphere, during the rise in the convection zone and at the loop apex, there will be diverging flows. And since these diverging flows are in opposite direction, they will experience the Coriolis force in opposite direction because of the rotation of the sun. And one of the foot point will be dragged towards the equator and one away from the equator. So that leads to the observed tilt in the active regions, bipolar active regions. Now, if you consider this flux tube, and they definitely will have the magnetic field, and because they are coming up because of magnetic buoyancy. Now, the two flux tube, one have a stronger magnetic field, one with lower magnetic field. What you can expect is that if the magnetic buoyancy will be higher in case where the magnetic field is very strong. So what it will do is that it will rise the flux tube very quickly. And if it is so, then the Coriolis force will not get sufficient time to tilt it. So what you can expect is that the rise time of the flux tube will depend on the strength of magnetic field in it, as well as since the tilt depend on the rise time. So you can expect that the tilt will be inversely proportional to the strength of magnetic field. So that was the motivation behind this work, to look for is there any observational evidence that we can get? But we have to be very careful that the B that they are talking about in this work is the strength of magnetic field at the bottom of the convection zone. And we don't have any observation at the bottom of the convection zone. So we cannot estimate what is the magnetic field value in the flux tube at the bottom of the convection zone. So now the question comes, what is tilt quenching? What is the why and how the tilt depend on the strength of magnetic field? But before I go into the tilt quenching, I'd just like to remind you that there's a work by Fan et al. In 1994 where they have shown that the tilt of bipolar active region depend on the strength of magnetic field as well as the flux. This is given by the relation that you can see here. Now, coming back to the tilt quenching. So if the tilt of bipolar active region depend on the strength of magnetic field, what you can expect is that there will be some, along with the Joyce law, there will be some additional term in the tilt relation that I have shown earlier in the Joyce law. And it is given by this relation that we have taken from the work by Lamberley and Sarvino and Karak and Message, and when Vidya Vinayakar was here as a Jacquetti fellow. So the idea comes from there. So in this, you can see that there is an additional term delta because Joyce law is very statistical law. So the Joyce law that you see is the statistical property. So you have to consider the scatter around Joyce law. So we have introduced delta. Now, what you can expect is that the tilt will decrease as we increase the magnetic field, and this will be more evident if your B in the flux tube is more than B saturation limit. And this phenomena is called the tilt quenching. Now let's look at the historical. Is there any evidence of tilt quenching in the historical work? And I was looking at the literature and I found that the work by Sibraman et al., Sibraman, Howard, and they have worked data from the Kodaikanal Solar Observatory as well as the Mount Wilson Observatory, and they have looked at the tilt of sunspot groups. So because they don't have a magnetogram observation, they have looked at the white light observation, and from that observation, they looked at how the tilt depend on the area of the sunspot. And what they have found is that as the area of sunspot is increasing, the tilt of the bipolar active region is decreasing. And that gives some indication of the tilt quenching. Why? Because we expect that the bigger active region, bigger sunspot will have the stronger magnetic field in it. So it's giving us some hint of the tilt quenching present in the active regions. Then there is another work recently by Maria Dasi, and they have worked on it's not visible, line is not at all visible in the plot here, but what it actually, if you look at the just point, it shows that the tilt normalized by the mean latitude is inversely, like it shows the negative correlation with the strength of the cycle. So in the stronger cycle, you have lower mean tilts. It's also give us some indication about the tilt quenching, that the mean tilt is slightly lower in the stronger cycle. Then in the simulation, the same I mentioned about Lamberley, Sarvino, and Karak and Message use these the tilt quenching relation that I have shown earlier with n equal to 2 in their model, and they have shown that actually their model is able to produce the mean observed behavior of the solar cycle. So these works have given us the motivation to look into is there any observational evidence we can get for the VMR tilt quenching. And so what we have to do is that we are looking for the observational signature of tilt quenching from magnetogram data. We have SOHO and STO that provides data from 1996 onward. So now we have almost 2 solar cycles more than 2 cycles of data. So we thought we will use the line of sight magnetogram data from these 2 observatories to look for is there any dependence of tilt on the magnetic field strength in the VMR. So first, what we have to do is that we have to develop some algorithm to detect the magnetic, like these active regions, these bipolar active regions from the magnetograms data. So just I'm briefly mentioning what is the algorithm of identifying the active region. So you start with the line of sight magnetograms. And what you do first, you have to do is that you have to do the projection correction. And the projection correction, for the projection correction, we are assuming that the magnetic field are completely radial at the surface. And then you have to just identify the intense magnetic field region using the adaptive threshold. And we have done is that, like, to identify the bipolar active region, we applied the flux balance condition, so that we are expecting that the flux in the flux balance condition will be satisfied in these active regions. So we have given some tolerance, like we are not expecting that it will be completely flux balanced. So we have given 40, 60, like 140, 160% till like tolerance level to while identifying these bipolar active regions. Then we have smoothed the magnetograms a bit with considering the PSF and the noise level in the magnetograms data. And after that, we have extracted all these parameters to look at how the BMR is, tilt of BMR depend on the maximum magnetic field in these BMRs. And this method is motivated by the work of Stemflo and Kosovicev in 2012, where they have used MDI data to identify the BMRs from the magnetogram and studied similar things, but not look at. So when we were looking for the tilt quenching, we looked at the Bmax distribution, just for fun, we have plotted the distribution of Bmax, and we found something very, very interesting. That distribution of Bmax shows double peak. So the first question comes, is it something to do with the instrument? Why we are getting two distinct peaks? Because if you look at the flux distribution, it shows that it's a log normal distribution, and we don't see this type of two distinct peak in the distribution of flux. So first thing is to check for the HMI, and it is actually present in the HMI actually. So now what is the region behind these two peaks that we see in the distribution of maximum magnetic field in the BMR? So to verify that, we look at all the BMR that we have detected. Interestingly, as we can expect, we don't see for each bipolar active region, you don't see any signature in the white light because it is lower flux as well as lower magnetic field, or it is also limited by the contrast and the resolution of the observation. So what we have noticed is that there are two classes of active region BMRs. In some of the BMRs, we see the signature in the white light images. You see the sunspot, but in some of them, you don't see anything. So then we segregated these two classes, and these two classes get well separated. So first peak is corresponding to the BMRs, which are very small, as you can see from this plot, that they are in very few hundred Gauss, peaking around 500, 600 Gauss in both the instruments, and another is around 2 kilogauss. So now the question comes, there are two different origins for these two classes? Are they coming from the two different classes of process in the sun? So to verify that, first thing that we looked at is the butterfly diagram. And both of them seems to follow the same butterfly diagram, provided the smaller one has larger scatter. And that is expected somehow because of the convection is playing a big role for the smaller active regions. And there will be convective buffeting in the effect on these, and they may have some scatter, and maybe other processes also playing role. But it's on statistical level, you can see that both of them are following the standard butterfly diagram. So that says that their origin, we cannot say based on this that they are coming from two different origins. To further verify it, we looked at the distribution of these two classes. Both of them follow the similar distribution, and both of them follow the Joyce law. So they are not also the ephemeral regions, because ephemeral regions, as per the earlier work, ephemeral regions show a large scatter in the Joyce law, and it's very difficult to recover the Joyce law from the ephemeral regions. So this also suggests that they are not coming from the two different origins. So based on this, we concluded that these two classes of BMR that we see, both of them are following the Joyce law, and they must have the same origin. So they are not coming from the two different origins. I will come back to this plot again in the later part of my talk. But our main goal for this work is to look at magnetic field dependence of the tilt. So here what we have done is that we have plotted the amplitude of Joyce law. So just to remind you, I am showing a gamma equal to gamma naught, that is the standard Joyce law. So what we done is that we have taken the Bmax spin. In each spin we fit the Joyce law, and then we calculate the gamma naught, and I have plotted the gamma naught with respect to the Bmax. So what you see is that initially the gamma naught is increasing with the maximum magnetic field in the BMR, but after 2 kilogauss, it is falling, systematically coming down. But at the same time, we have to keep in mind that we have only just 3 data points where we can see the indication of decrease in the amplitude of the Joyce law. So there are some indication of tilt quenching. But interesting part is the first half. So below 2 kilogauss, we see the increase that was not expected, and we still don't have the answer for that. Why we expect? There are some work that also suggests this type of behavior, but based on the simulation and models, we don't have the proper answer. Why should we expect the tilt should increase with the maximum magnetic field in the BMR initially? In the later part, where we expect the tilt quenching is present, but again, we have only 3 data points, and we have to wait for the stronger cycle to get more data points. Or another way is to again look at the historical data and somehow get the proxy of magnetic field and estimate these. Along with that, we also looked at a similar thing, but instead of maximum magnetic field with the flux. But again, this is not. So we see the decreased trend in MDI, but not in HMI. So it's consistent with the finding of Stanflo and Kosobe. They have also looked at the dependence of tilt on the flux. And based on similar result, they concluded that thin flux tube model is not, doesn't exist. So there is a Boulder statement in their paper that based on this result, they have concluded that, but we have to be very careful that the tilt not only depend on the flux, that's Bmax, there are other parameters also play big role in the, while deciding the tilt of the BMRs. So we will not talk much about the flux because we don't have much significance and we don't see much variation in this particular part. So statistically, looking at the statistical significance of these variation, we have stopped here and we will not look into the flux and we will not discuss more about the how it depends on the flux because we have to look for the another way to get more reliable result from the flux. But the tilt quenching part where we see that how the tilt is strength varying with the maximum magnetic field in the BMR. So here what we have done is that we have looked at the mean and then we have fitted the equation that I have shown earlier, Bmax by B saturation and we have, because we have very limited data points, instead of using the standard least squared fitting or any other fitting, we went with the Bayesian approach and where you see the distribution of B0 and N, and you can see that the mean of that distribution is around 3 kilogauss. So what you can expect is that the B saturation value that we have mentioned, I have mentioned earlier, is around 3 kilogauss, and the N is around 5.5. So that is far greater than the one that has been used in the simulation by Servanov or the Karakan missiles. So it was even more supporting the idea of tilt quenching because you have even higher tilt quenching if you have the value of N as 6. So based on this, we can say that the tilt quenching is present and we get some indication of tilt quenching from the active region study that we have done using the magnetogram data from STO and so on. Now, at the same time, we have also looked at the scatter around the Joyce law, and this result is like very convincing that you can expect that this scatter around Joyce law will decrease with the Bmax because if the magnetic field is very strong in the active region, what you can expect is that it will be less affected by the convection, and that is very evident from the Bmax as well as the flux. So it's a very familiar result to all of us. Now, there are some questions related with the work. First is that like when we have looked at the bipolar active region, we have counted single active region many times. So why is that? Because we have detected, we have not tracked the bipolar active regions. So if you are not tracking, you are counting each active region as a separate one. So one can expect that the two peaks that we are getting could be that different phase of the same BMR. And another thing is that when you talk about the tilt, how will you decide in which phase? Because there is a work by Hannah Sankaran from the Max Planck. They have shown that the tilt actually varies with the lifetime of the BMR. If that is the case, then the result that we got here may have some effect of that. We have to track the active region to get the proper. Now, once you track, if the tilt is evolving, you have to also decide in which phase you take the tilt of the BMR. So, to answer all these questions, we have started looking, or the double peak that is either something to do with the observation, or is there an observational bias in the instrument or something there that we are getting these two peaks. And if we able to track the BMR, we can also answer some of the other questions that is not related to the work, that is how the tilt, Bmax, and flux of BMR varies over its lifetime. Definitely that will be very interesting to look into validation of the flux tube model. So the answer to all these questions was track the active region and follow them. So if that is the case, is the question, we have came up with another algorithm that has been recently developed in the collaboration with Bigda Vinayakarak, one of his student, Nusri Devi, and we have developed one of the algorithm that is just came today. It came online, and but it was expected accepted in few months back. So we call this algorithm AutoTab. So its algorithm is called automatic tracking algorithm for VMR. So this algorithm has three major steps. One is the detection that I have already discussed, and then there is a pre-processing step and the tracking. The beauty of this algorithm is that it is not limited only to the VMRs. So if you have a detection, your own detection method or any type of feature, and then you can slightly tune based on the type of feature, you can pre-process your data, and then you can use AutoTab to track any of the features, starting from sunspot, coronal holes, or any other feature present on the sun. So this code is not right now public, but it will be available publicly in the future. So then I will briefly talk about the pre-processing stuff, particularly for the VMR point of view. So in the VMRs, the detection process only gives you the boundary of the active region. So the problem is that in the boundary, there are some fragmented structures. So when you are tracking, you have to be very, very precise, because during the maxima, you have a lot of active regions. And if there are a lot of active regions, it's very difficult for the algorithm to identify if these are the same active region or not. So there is another way to track is that go to the Carrington frame. But we avoided that because when you do convert your images into the Carrington frame, what will happen is that you are doing some type of interpolation. And if you are doing interpolation, you are playing with the numbers. And it depends on the type of interpolation you are using. So that's why we decided we'll not go with the Carrington frame. We'll keep ourselves in the full-disk frame or in the Stonyhurst frame and track. So the first step of pre-processing is just to get again, inside those boundaries, that rectangular region that you see here, get the pixels where value is greater than threshold so that you can get rid of the other background and outliers. And then you have to somehow, we have used the more logical operation to fill those gaps. And after that, you will get this boundary. It's not clearly visible here, but the white lines are not properly visible, but it's just to say that you're redefining the boundary of that region. That's the main purpose of pre-processing. So then what we have done is that we have used the feature association technique to track the VMR. So here I'm showing you the one example here where we have selected one active region. So what you do is that you select one image and you calculate the longitude of that image. So you know that when, based on the differential rotation profile, you know that when that active region is expected on the west limb. So during that period, whatever observation you have, you track that active region in that. So, and then you look for the overlapping of feature, flux difference, and everything. And based on that, we have tracked these active regions. So we keep on. So sometimes what happens is that due to the limitation in the detection and the noise level in data, you miss some of the active regions. So you keep on tracking. In few of the images, you miss them, and then again they come up. So that's the reason what we have done is that we have keep on tracking till it reaches to the west limb. So by this way, we have avoided such cases. So here I'm showing you to just briefly the algorithm of automatic VMR tracking. So then I'm just showing you one example where I'm showing the evolution of VMR. Again, the color is not looking very proper in this. But if you look at how the tilt and the maximum magnetic field in the VMR is varying, you can clearly see that the Vmax, if you choose in the different stages, they are not same. They are very different. So you have to be very, very careful while picking the tilt or the maximum magnetic field or any other parameter of the bipolar active region. You have to be very careful and you have to properly define what is your definition, or because there is no standard definition about in which page you should pick the tilt or Vmax of the active region. Now this, as I mentioned, this just yesterday it came online. This is the paper that I have just talked about. Now the question was like that I had posed earlier about the bimodal distribution of the Vmax. So as I have shown you earlier, this is the plot. I'm just showing here the MDI. Is it present even if I track the bipolar active region and just take each active region only once? And if we do so, again, this is present, but the numbers are very different now. because you are counting each active region only once. And another thing that just I will just add a caution here that just because this work has been done by a PhD student, I have noticed that there is some scaling, as you can look at the two plots, that there is some scaling difference. So we have just noted that during the projection correction, there are some term that has led to this scaling that you can see, like there are some magnetic field even beyond 4 kilogauss, but in the first plot, it is not much. And even for the MDI, around 3 kilogauss is the saturation limit. So in MDI, you cannot trust the magnetic field value above 3 kilogauss. So, but still, if you for a time being, if you just forget about the x-axis and if you just look at the distribution, you see that the bimodal distribution is present there. So now it's the question for the theoreticians and others to why we see the modelers, to why we see the two classes of BMRs in the sun. We don't have the answer for that yet. And again, let's come back to the tilt quenching based on the tracking. So now what we have done is that we are defining the tilt of BMR by, we are taking the tilt when the flux is maximum in the BMR. So we track the BMR for throughout their lifetime and all the disk passes, and we looked at the flux. So when the flux of BMR is maximum, we say that that is the time where we look at the tilt. And based on that, again, if you look at the tilt variation with the Bmax, we have to be a little careful with this because statistics is very poor in this case. Again, as I mentioned, so since we are not counting active region many times, we have limited number of active regions. And when you are doing the such and when you are winning it in Bmax, you are even reducing the statistics. So this is very preliminary result. So that's why I have marked there but it still indicates the similar trend that we have seen in the earlier work, even after tracking the active regions. So now when you start study the BMRs, what is the problem is that like you are not seeing all BMR throughout their lifetime. Because of the limited observation, you are only seeing the half of the sun. So when you analyze, when you study the BMRs, you have to be very careful. You are not picking up all the phase of the BMR. So how will you decide the tilt? How will you decide the Bmax and flux and everything? So to minimize the effect of that, what we have done is that we have classified our BMRs in 3 different categories. One is the short-lived. So short-lived are the ones where the lifetime of the BMR is less than 8 hours. You don't see in more than like 5 or 6 images because MDI provides the cadence of 96 minutes. So 8 hours means you are not seeing more than 5 or 6 images, data frames. You don't have that more than that. So they are very short-lived and their flux is very low. I will come to that again. And then another class that we have given is the lifetime class. So these are the BMRs which emerges in the near side and decays in the near side. So we have the full information about these classes of the BMR. So we have tracked them throughout their lifetime. And there's another class, we call it a disk passage, where we only know the partial phase of their lifetime. Either they are emerging in the far side and decaying in the far side, or like decaying in the near side, but it's emerging in the near side, but it is crossing the west limb. So we are not able to track them in the point below, like beyond that point. So what we have seen is that our 14% of BMRs are falling in the short-lived classes, and around 35% is in the lifetime, and the disk passes class are actually 51%. So there are a lot of BMRs which is expected. So because it's considered a lot of other, like emerging in the far side, decaying in the far side, emerging and decaying in the far side. And even if it is emerging at near the west limb in the few days, you will see that they are going in the far side and you are not able to track them. So what we have done is that we have just looked at how the flux and other parameters are varying in these three classes. So you can notice that like in the first plot that in the top panel, we have only 5 data points. As I mentioned, and it's decreasing. So flux, Bmax, both of them are decreasing with during the evolution of the active region. And then if you look at the second panel where we have to look at the flux and Bmax, you see that these are the lifetime classes of BMR. You are seeing increase in the flux and then decrease in the flux. And at some point you stop like you lose track of it, the BMRs, either because of the flux balance condition is not satisfied and it has decayed and you are not able to track them, identify them. And the third class, that example that I'm showing here is like it has a very high flux when it emerges in the east limb, but it is decreasing. And Bmax as well as the flux, both of them are following similar trend. So these are the three classes. Now, when you look at the butterfly diagram for these three classes, first thing that you notice the color difference. So color definitely the short-lived ones are the very small BMRs. They have very low flux. And lifetime VR is reasonably in between the disk passes. And the short-lived ones are not strictly following the butterfly diagram. As I have mentioned earlier as well, that small BMRs, they are not actually following the butterfly diagram that strictly, but still you see some butterfly-like trend there. But as we come to the lifetime class BMR, you see more clearly the butterfly diagram. And if you go to the disk passes, they are perfectly following the known butterfly diagram that we are aware of. So this again suggests that they are like the convection is affecting much to the shorter class. And when you talk about the tilt and other parameters, you have to be very careful while deciding the tilt for the short-lived BMRs. And then we looked at are they following the solar cycle behavior or not? So here we have plotted the number of BMRs, such classes of BMR, along with the standard sunspot number. And what you see is that short-lived are also not following the sunspot. So they are emerging all the time. They are not following the solar cycle behavior. Lifetime class is following the solar cycle behavior, but interestingly, after 2016, you see that in the HMI, we see a lot of lifetime BMRs as well. But if you go to the disk passes, it is perfectly following the solar cycle behavior. So what you can see here is the sunspot that we see is actually the disk passes class is actually the sunspots that we see. They are big BMRs. They are only producing contrast enough in the white light images to detect them as a sunspot. And now I come to almost end of my talk for this particular part that we looked at the evolution of the BMR. And so this plot just we got a few days back, and there are a lot of information here, but I will go very slowly here. That in the first plot, what we have done is that in the first panel that you see in the left side is the evolution of BMR, tilt of a BMR with their lifetime. So here we have normalized the lifetime. So why this is important? Because all the BMRs doesn't have show the similar lifetime. So what you have to do is that what we have done is that we have taken all the lifetime class BMR. So lifetime class BMR are those, again, I will remind you that they are BMRs which emerges in the near side and decays in the near side. So they have a lifetime of around 6-7 days. And so what we have done is that we have made their lifetime as a 1 day. So whatever is the maximum, we make it 1 and then normalize all of them to 1 day. And then we have plotted the tilt at the different phase. And what you see is that the tilt is initially increasing and then it is saturating, but there is some dip in between around 0.6, like around 60% of their lifetime. So that we don't know why is that, and this is the smooth curve that we have plotted, but it is in agreement with the thin flux tube model that initially what you expect is that the tilt will have some, and what you are seeing only the top part of the flux tube. And that's why tilt is not properly defined at that time. So you have to wait for some time to get the proper tilt, and that we can see here. But one can give another argument that tilt is the local phenomenon. So it's not coming from the bottom of the convection zone. And that's why you don't see when the BMR emerges, they have very less tilt. And as they stabilize, you see the saturation in the tilt. Another interesting thing is that, like, if you look at the B mean and B max, what you see is that initially B max is high, it decreases and again increases. So B mean, why we can expect that because you have a smaller BMRs, your average will have the higher value. But as they disperse and then they will have the lower value, and at the end of the time, it's still like the BMR has dispersed a lot, but there are some fragmented structure where you have a larger value of magnetic field, and that's why we are expecting its Bmax, but still we have to look slightly deeper into that in the end phase of the why B mean is higher at the end phase of the BMRs, and similarly for the Bmax as well. But the foot point separation, that's again to verify test the thin flux tube model we looked at, and what we see is that the foot point separation is increasing. Initially, it is increasing, and then it's saturating, and that we can expect as the BMR emerges, their foot point gets separated, and after some time, don't see much change in their foot point separation. So this is the work that currently in progress. This is a very, very initial result. We are still looking into the different way on these numbers. And maybe in the future, in coming months, you will see that on the archive, but still we are working on this particular part. So that brings me to the summary and conclusion of my talk. So main motivation of this work, as I mentioned, was to look for the tilt quenching. That is how the tilt of BMR depend on the strength of magnetic field. And while doing that, we found something very, very interesting, that the Bmax saw the bimodal distribution. And it has been verified by another work that we have done recently by tracking the active regions. And so we don't have the answer for that. Why there is a bimodal distribution of the BMR, Bmax saw the bimodal distribution. And when we talk about the tilt quenching, what we expect is that around 3 kilogauss, you will start the effect of tilt quenching. So only in the bigger active regions, you will see the effect of tilt quenching. Now it's the simulation, we can try with this saturation in the simulation and see how it can affect the study of the solar cycle. So I will just leave you with this slide. It's not looking good, but it is the current simulation with the data simulation of the sun. So you are looking at the two poles of the sun. So we are both very close to the polarity reversal. It is related with my current work. So it's not visible here, but you can see the dates. So it's currently our sun, and we are very close to the polarity reversal. So maybe in 6 months or in 1 year, we will see the polarity reversal in the both hemisphere. And we are expecting that there will have around 6 months of delay in these, again in the polarity reversal of the two hemisphere. So thank you for your attention, and I will be very, very happy to answer any of your questions and comments.
Thank you. So questions from the room and online people also, you can ask your question. Greg?
Yeah, wonderful talk, Prabhuti. And well, I want to see this little video that you're showing right now go forward past the present day and see the future. But
yes.
And more seriously, the general evolution that you showed 1 or 2 slides ago.
Yeah.
Why did you combine the 3 different lifetimes into the same plots? Because I would think they would all have fairly different evolutions in terms of the angles and the separations of the foot points. Yeah,
So,
that one there. So you said you'd combined all 3 of the different classifications you'd given the BMRs into these composites.
In this, like I have mentioned, that we have only taken the lifetime classes of BMRs, where we have the full phase of the BMR evolution from the emergence to the end phase.
That's what you meant by lifetime. I figured you meant sort of the 8 hours, the 14 days.
Yeah.
Okay, good.
In this analysis, we have not included the disk passage and the short-lived ones, so only lifetime classes.
Yeah, okay. Thanks, my misunderstanding there. Yeah, thanks again, Prabhuti.
Thank you.
Other questions? Yuhang?
Yeah, yes, thank you for a very interesting talk. I just question about the bimodal distribution of the Bmax. I understand that measuring magnetograms, these magnetograms measure flux density, not the intrinsic field strength of the flux elements or flux tubes. So what you are measuring is sort of like has a filling factor effect in it. So you're probably measuring, I think, would it be reasonable to think that you're measuring 2 types of filling factor distributions? 2 types of filling. Well, the one with the sunspots, you're basically measuring maybe for filling that's near filling factor 1, you're truly measuring maybe the intrinsic field strength. But then for the the other type is probably the decaying activity, which there's no sunspots. Then you are measuring the cases where the filling there are, the decaying activity, lower than 1 filling factors, and then the peak would be maybe something to do with the supergranular lane kind of situation where you see a peak field strength. That's the typical peak field strength you see. Would that be?
It's around 600 Gauss that we are seeing in both the instrument. But if you consider HMI, because there is a scaling factor between HMI and MDI. Again, I agree with the point that, like you have mentioned about the filling factor, and it could be possible that in the two different cases, like we haven't thought about the filling factor, so thank you for pointing that out. But the another point that you have mentioned about the decaying active region. So these classes are not the decaying active region. That's why you don't see the sunspot. It is because their flux is very low and they are emerging and they are not strong enough to produce the contrast to see it in a white light images. So because we have tracked it now, so we have a lifetime. So it is like throughout the lifetime. So again, one part of the work that we have still not done is that, like, during the evolution, we can look at when we see the sunspot and at what time of what is the lower flux or the maximum magnetic field in the BMR, at which point we see them as a like sunspot in the white light images. But they are not, all of them are the diffuse flux that we see at the end stage of the BMR. They emerge with very low field and they are decaying with the very early, like in few days, or like even I have mentioned about a few hours. So, but again, thank you for pointing out that filling factor. So we definitely look into that, how the filling factor will vary in the different classes of active region, and we have to carefully look into it. And another point that you have mentioned, we are not actually measuring the Bmax, so it's flux density we are measuring, and that is like depend upon what is your filling factor. So I missed that point to mention that, but yes, so we are aware that it's not the maximum magnetic field, it's the maximum field density, flux density, we can say more appropriately.
Thank you.
Other questions?
Still concerning the bimodal distribution, when you show the two different histograms, you apply a correction so that you do not count each more than once, right? What?
I didn't get you.
Remember that you showed another one that
Yeah, so
that one.
this one.
Yeah. I mean the second bit decreases more because you're counting more time because it has a longer lifetime, or what?
Yeah, so in the second class, it is the fact that your bigger BMRs will stay for longer period.
So you're counting more.
So you're counting more time. But the second one that you have seen, that the second peak has decreased a lot after the tracking. So yeah, definitely that is the point, because it is we are counting many times, and that biasness is increasing as we go from the lower flux to the higher flux. But in the second case, that is not, after tracking, it is not the case. So that's why you see the larger dip in the second class.
Anyone from online or hall? Okay, if there is no other question, let's thank our speaker again.